the heat now for the juice to melt in the ice, and if that heat is less than this, then it's going to get heated more. If this is greater than that, then we'll have ice left over and the final temperature is 0. So it's usually easier to, but we'll see when we get to the second law that sometimes it is useful to take away some from this point, from here, and then mix them together. Now you could have done that if you wanted to here, but I don't know why you really want an intermediate temperature. You could say, well, it melts, but we didn't have mass it, so that was good. The point is that the overall temperature will be ice at 0 to water at 50. But I've done it 2 steps. Melt the ice and now raise the temperature of the water from 0. And that's the way it is. As long as you have ice with the water, the temperature is 0. Once you have no more visible ice, it might be just 0 or higher. So that's really, so if you ever have a problem, and it says, indicates to you that ice and water are both present, then you know that the final temperature is 0. No calculation necessary. If you're in the kitchen, you want to make 0-degree temperature water, you take some water and add enough ice and stir it until the ice doesn't melt anymore. And then even without a thermometer, you know it's. Now if it's just at the brink, then it could be 0 with no ice. If it's a little bit more ice, and you see it stay. So what if I want to get rid of the ice anyway? Just turn it off, filter it off, put it through the funnel, and now you'll have 0-degree water. Now the last one, if I have time, I'd like to look at is one where we're going to have heat and work. We're going to calculate delta E. Given this, water liquid becoming water gas at 100 degrees Celsius. 1 atmosphere pressure. I'd like to shout delta E. Find delta E for vaporization of 1 mole of water at 100 degrees Celsius, 1 atmosphere. Now, I look on the table and I find that at the boiling point, the standard heat of vaporization is, if I can't find that, I'll be so it was around 43. I did have it. I don't have it. If I have it, here it is. For water, the standard heat of vaporization at the normal boiling point is 40.79 kilojoules per mole. That is delta H naught of vaporization plus 4079 kilojoules. No temperature change because it's at 100 degrees. What I'd like to do is to find delta E. Now remember, delta E is Q plus W, right? Delta E is Q plus W. Well, why not I calculate W? I'm going to calculate work. What's the heat? If I calculate work at 1 atmosphere pressure, what's the heat? What's Q? If I calculate the work at 1 atmosphere pressure, what is the heat? At 1 atmosphere constant pressure, what is the heat? Thanks. This is the heat. It requires, when it evaporates at 100 degrees 1 atmosphere pressure, it requires 40,790 joules per mole. This is Q. So I said, let's try to do that. Let's do it on a mole. Why do it on that now? And now what I'm going to do is I'm going to calculate the work. I'm going to say, work. What's the work? Let's calculate the work. Remember, we don't usually measure the work with thermometers, but well, we usually calculate the work. So find the work. So what am I going to do? I'm going to evaluate D2 and D1. D1 is about what? I have a list.